Hello everybody, thank you for coming. I hope you are all doing well. My name is Isaac Polinsky. I am a PhD student in the Whisper Lab at NC State, and today I'll be presenting NM Variant Systems Adversarial-Resistant Software Rejuvenation for Cloud-Based Web Applications. As a security researcher, I often look at trends for inspiration. For example, every year FireEye publishes a review of all their incident response investigations in a report called M-Trends. One metric they define in these reports is the concept of dwell time, which is how long an attacker spends in a network before being detected. As you can see from this graph, over the past 5 years, the median dwell time has gone down from over 140 days in 2015 to 60 days in 2019. In fact, the outliers are even more alarming. In 2017, there was an incident where an attacker went undetected for over 5.5 years, and in 2019, an attacker went undetected for just under 8 years. As we get better at detection, I wonder if we will ever be able to get this number down to 0. Minimizing dwell time is the motivation of this research. Assuming the attacker has compromised a vulnerable server and is able to maintain persistence, how can we reduce the amount of time the attacker is in a network? The naive solution is to periodically refresh servers to a known good state. In fact, this solution works well in cloud environments because we can leverage properties of the cloud. For example, most cloud environments will boot instances from read-only images as they're needed, meaning the instance is in a known good state. Using this property, it is easy to imagine that if we refresh the instances on some interval, we will remove the attacker from the system and limit their dwell time. Once again, this is a naive solution, and we want to look at this more deeply. Let's assume the attacker knows we are refreshing servers. How might the attacker maintain their persistence? Since we are losing local file system changes on every refresh, the only way to persist is by corrupting persistent storage, such as a SQL database that is connected to the server. By corrupting persistent storage, the attacker has an opportunity to automatically reinfect fresh servers when they read from this storage. To account for this issue, we revisit our research question. How do we reduce the amount of time an attacker can be on a given server and prevent automatic reinfection? To answer this question, we must find a way to protect persistent storage. Our intuition is to use output voting, which is the idea of standing up functionally equivalent but somehow diverse systems and comparing the outputs for a given input. In the context of a web server and persistent storage, this means creating diverse servers and comparing the SQL queries from each server to the database. If these queries match, we allow the action to proceed. Otherwise, we prevent the action and perform some recovery steps. Note the importance of diversity. It prevents an attacker from simultaneously compromising all servers in the same request and beating the voting system. This idea of software diversity is core to a lot of previous works, such as N-version programming, N-variant systems, or more generically, works in the fields of multivariant execution environments and Byzantine fault tolerance. The key idea of our research is to leverage this broad history of fault-tolerant systems and deploy them in a cloud environment to protect vulnerable web servers. However, there is one problem in common with the previous approaches in these fields. When unanimous voting is used and voting fails, the entire system goes offline and request processing stops. We believe that unanimous voting is important for providing the strongest security guarantees. Our goal is to build a fault-tolerant environment that has resilience to attacks, but we also want to continue processing other requests when voting fails. This leads us to the contributions of our work. We extended the concept of N-variant systems into NM-variant systems. This new parameter M configures the amount of redundant resources in the environment that allow the processing of other requests when voting fails. Additionally, this parameter provides a tuning knob for administrators to balance performance overhead with their risk tolerance. With the goal of NM-variant systems in mind, let's walk through how we integrate a web server into an NM-variant system environment. Here's your typical web system. There is a pool of servers running on virtual machines. These servers are receiving requests from the internet, likely through a load balancer. And while processing these requests, the servers interact with persistent storage. For example, a database or a cluster of databases behind another load balancer. The first step is to break down the server pool into N pools of M servers, where each of the N pools is referred to as a variant pool and consists of servers that share no vulnerability with servers in other variant pools. Next, we add a scheduling proxy, which acts as a special type of load balancer, forwarding requests from the internet to one server in each variant pool. And finally, to do output voting, we add a verification proxy, which sits transparently between the servers and the database to compare the queries. If the queries from each server match, it allows the query to the database and copies the response back to all the servers. However, if the matching fails, the verification proxy triggers a recovery action. Now that we've transformed our environment into an n invariant system, let's quickly walk through an end-to-end example for a 2-3 variant system. First, we have a request from the internet. This is going to be received by the scheduling proxy, and a scheduling proxy is going to select a serving set, which is one server from each variant pool. Next, the scheduling proxy creates a unique identifier and forwards the request to the chosen serving set. The servers receive this request and begin processing, and as part of processing, they send queries to the database. As you'll notice here, the query to the database has the same unique identifier that the scheduling proxy sent, and we'll talk about this more later. Once the verification proxy receives a query from every server in the serving set, it performs a comparison. If the comparison succeeds, the request is forwarded to the database processes the query and generates a response. This response is then forwarded back to every server in the serving set by the verification proxy, and processing continues. Note, as part of normal operation of a web server, there will be more than one query to the database, and each query is going to follow the same process of the verification proxy. Once processing is finished, the servers are going to generate a response back to the scheduling proxy. The scheduling proxy is going to receive all the responses and send a single response back to the client on the internet. Now let's go into more detail about how each of these components work. First, we have the scheduling proxy, whose goal is to minimize the chances the adversary has at making changes to persistent storage. This is achieved through three responsibilities: selecting a serving set, refreshing servers, and tagging requests. Serving set selection, or how we choose servers to process an HTTP request, is an important step for introducing uncertainty to the attacker's plan. As we'll see later, for performance reasons, we will be reusing servers to handle multiple requests, and this can be exploited by our adversary. To prevent an adversary from guaranteeing which server or servers will be processing the request, we randomly select a server from each variant pool. This was based on our theoretical analysis, which will be discussed later. Also note, if all servers are offline for recovery, we simply respond with HTTP 300 service unavailable. The next responsibility is routinely removing infected servers by rolling them back to a known good state. This is the concept of software rejuvenation, or as we've been calling it, refreshing. Refreshing can be done in two ways. Reactively, when we detect something has gone wrong, then we can roll back all the servers involved, and proactively, when we perform refreshing on some interval. This can be tied to wall clock time or request rate. In our system prototype, we asked the administrator to define a parameter k, and on every request, k servers are chosen randomly to be refreshed. By combining reactive and proactive refreshing, we can further introduce uncertainty to the attacker's plan. The final responsibility of the scheduling proxy is to uniquely tag HTTP requests. When handling multiple HTTP clients simultaneously, it becomes difficult to perform output voting. If there are R concurrent HTTP clients, then a verification proxy may receive up to R times N SQL queries at one time. So how do we know which queries should be grouped together and compared? We address this by generating an unforgeable tag that uniquely identifies an HTTP request. We then place this tag in the IP options of the IP header. However, one additional problem is that we are tagging HTTP requests and a verification proxy is comparing SQL queries. So we need to propagate these tags to the SQL queries. To address this problem, we use a variant pool host agent to correlate HTTP requests to SQL queries. This process runs on a potentially compromised host, so we cannot trust it at all. Luckily, we only rely on a process to map incoming requests to outbound queries, and since our tag is unforgeable, we do not need to worry about the untrusted process tampering with or trying to replay the tag. Likewise, if the host agent fails to do its job and propagate the tag, we can easily detect this at the verification proxy. The final component of NM variant systems is the verification proxy, which implements the output voting that protects persistent storage. First, we group the queries by unique tags, and then we perform a comparison. If the queries match, we allow the query to proceed to the database and copy back the response. However, if the query fails, we trigger a refresh on all the involved servers. During comparison, we do need to be careful about how we handle non-deterministic fields. For example, timestamps, which are expected to be different in distributed environments, must be accounted for. We handle this by asking the administrator to provide a list of non-deterministic fields which we can ignore, and then we perform a simple string comparison. In our test environment, we were easily able to identify and extract these fields. Now that I've described how NM-variant systems are built and how they operate, we want to answer the following 3 questions. What makes NM-variant systems secure? What is the performance overhead? And how should we tune our parameters? We started with a theoretical analysis to understand which parameters make our system secure. And we did this by simulating an optimal attack strategy against different parameter configurations and recording the number of requests until the adversary succeeded. An important assumption made for this analysis is that the attacker cannot compromise more than one server with a single request. More details can be found in paper, but we summarize the following 2 takeaways here. First, proactively refreshing servers more often resulted in a substantial increase to the number of requests until compromise. And second, adding more variant pools, or increasing N, made the adversary's job slightly more difficult. Next, we built a system prototype and measured the overhead on throughput and latency with 2 experiments. In the first experiment, we compared the NM variant system without refreshing to a vanilla web server to get the idea for the raw overhead. And in a second experiment, we compared different N, M, and K configurations to understand each parameter's impact on performance. Once again, more details can be found in a paper, but we summarized the key takeaways here. The main takeaway is that frequent access to persistent storage results in high overheads compared to the vanilla baseline. For example, for different configurations, we observed up to a 38 request per second drop in throughput and up to a 1.5 second increase in latency. It is important to stress that this overhead is dependent on the application itself. Applications that generate more queries will have higher overheads, as we see here. Next, we noticed that increasing N resulted in lower throughput and higher latency due to bottlenecking at the verification proxy. As we increased the refresh rate, we observed lower throughput and latency due to fewer servers being online and less contention for resources at the verification proxy. Finally, we saw that increasing M allows you to maintain a slightly higher throughput for higher refresh rates. With all these takeaways in mind, we wanted to know how we should guide an administrator to tune their system. We performed yet another simulation where we varied the refresh rate and pool size, and then fit a curve to the median request until compromise. Using these equations, we visualized the security guarantees and wall clock time. We once again refer you to the full paper, but we summarize the results here with a demonstration. Consider a simplistic environment that receives 10 requests per second. If the administrator assumes a determined adversary is only able to send a max of 1 request per second, or 10% of the total traffic, we can use the equations from the different environments to calculate a period of resistance and wall clock time. For example, with n equals 2, you can see for lower refresh rates we can only hold off an attacker for under a minute. But as we increase the refresh rate, we can hold them off for almost 5 minutes. Likewise, with n equals 4, low refresh rates give us a window of just over an hour, and increasing the refresh rate gives us over 5 years of defense. This time can be critical. For example, it may complement heavy IDS systems, effectively defending against attacks until the IDS can process its backlog, or it may allow for human intervention, giving enough time for a security analyst to detect and respond to attacks before they're able to succeed. Finally, remember that we assume a sophisticated attacker that is fully aware of our defenses. In summary, we showed that NM variant systems can put an upper bound on adversary dwell times. Our system can prevent adversary persistence by blocking malicious writes and allows for continued processing of requests while recovery actions are being taken. We can tune our system to fit your cost and risk tolerances, and finally the resultant delays to adversary success can be used to complement slower or overwhelmed IDS systems and security analysts. Thank you.